Welcome to the presentation of my article, Modeling Climatic Temperature Using the Stability Solution. I'm Dr. Kevin Woods, and this article is published in Prose Journal of Heat and Mass Transfer, which is available at prosejournals.com. Claims in academic textbooks differ relating to climate, but have a general theme to them. For example, from Chang's chemistry textbook, he claims the Earth would be 30 degrees cooler without carbon dioxide, while other textbooks like Thermodynamics from Chengel and Bowles claims that the greenhouse effect causes Earth to be 30 degrees warmer. Similar claims are made by other textbooks, but the general summary of it is the atmosphere and clouds cause Earth's surface to be 30 to 33 degrees Celsius warmer. However, all of these claims are wrong. The basis of these incorrect claims is the blackbody radiator model. It's a rudimentary thermodynamic energy balance that sets the Earth as a system, with a system boundary located above the atmosphere. An energy balance is applied on that system boundary, which equates the sunlight coming in minus the sunlight that's reflected, which is about 30%, to the heat emitted by the Earth. When you solve, you get the temperature of the Earth. In equation form, the energy balance has solar absorbed, which is shown on the left here, equated to heat emitted, which is shown on the right. This is the Stefan-Boltzmann equation. The constants are shown as such, with the Earth's albedo being 30% and the blackbody radiator emissivity is 1. When you solve for the temperature, you get negative 18 degrees Celsius, and this is compared to the measured average surface temperature of the Earth, which is 14 degrees Celsius, leading to a difference of 32 degrees Celsius. This is where the 30 to 33 degree number in the claims comes from. However, the solar reflection and heat emission maps shown provide conclusive evidence as to why the claims are wrong. These maps are determined from satellite data from above the atmosphere, which is where the system boundary is located. It is evident that the albedo includes clouds, atmosphere, and surface, but mainly clouds. It is also evident that the heat emission includes clouds, atmosphere, and surface. So the negative 18 degrees Celsius is a combination of clouds, atmosphere, and surface temperatures, not the surface temperature without clouds and atmosphere. This concept is clearer if we zoom into the system and system boundary. The system boundary is located above the atmosphere, and the system is comprised of clouds, atmosphere, and the surface, all of which are emitting heat. However, the heat emitted by the surface is predominantly absorbed by the atmosphere and the clouds. Therefore, the negative 18 degrees Celsius is a combination of mostly clouds and atmosphere, with a little heat source from the surface. The blackbody radiator model assumed all heat is coming from the surface, which is evidently incorrect. A more proper thermal model removes the clouds and the atmosphere and the parameters of the equation and assumes the Earth as a gray body radiator. The albedo is that of the surface at about 10% or 0.10. Also, the surface emissivity is 96% or 0.96. Solving yields 1 degree Celsius for the surface temperature. And comparing to the measured surface temperature of 14 degrees Celsius, the conclusion is that the actual greenhouse effect is about 13 degrees Celsius, not 30 to 33 degrees Celsius. What we can conclude from the gray body radiator model is that the claims made in academic textbooks have no basis and are wrong. To be able to delve into what parameters affect the greenhouse effect, the next section will build on the gray body radiator model, adding atmosphere and clouds into the modeling to determine realistic claims. To start, the clouds are removed and the surface and atmosphere are separated into two energy balances. The surface energy balance starts with the gray body radiator model and expands to include parameters such as solar absorption by the atmosphere, Rayleigh scattering in the atmosphere, and atmospheric heat emission towards the surface. The atmospheric energy balance equates the emission by the atmosphere, which occurs up towards space and down towards the surface, to the solar energy absorbed by the atmosphere, plus the heat emitted by the ground that is absorbed by the atmosphere. To now, only radiation heat transfer has been considered. However, evaporation and convection occur across the system boundary between the surface and the atmosphere. Evaporation and convection are integrated into the surface and atmospheric energy balances as a heat flux quantity, removing heat from the surface and adding it to the atmosphere. Solving for the surface and atmospheric temperatures yields the following equations. The unknown is the heat flux from the ground to the atmosphere for evaporation and convection. However, this is solved using natural convection theory. Atmospheric air circulation is driven by water molecules evaporating into the atmosphere at the surface and condensing in the atmosphere at higher altitudes. Adding molecules to a gas at constant volume and temperature increases pressure, while removing molecules from a gas at constant volume and temperature decreases pressure. The pressure gradient created generates circulation cells in the atmosphere, consistent with natural convection theory. The evaporation and heat convection from the atmospheric circulation is quantified using Newton's law of cooling for heat and mass transfer. The heat transfer quantity is on the left. The mass transfer quantity is on the right. When the equation is expanded, the driving force for the circulation is delta rho, quantified as the condensable fraction in the convective flow. This condensable fraction is the concentration of water vapor at the surface minus the concentration in the atmosphere, determined using the Clausius-Clapeyron equation. It should be noted that the factor F sub W is added to the mass transfer part of the equation to compensate for the fact that certain areas of the Earth do not allow for evaporation, such as deserts. Integrating all equations together yields the three-equation model. The first equation is the surface energy balance, the second equation is the atmospheric energy balance, and the third equation is the equation of heat flux for evaporation and convection. Solving these equations simultaneously produces the following temperatures and heat fluxes. It is evident that the model is converging on the measured average surface temperature of 14 degrees C, as the calculated temperature is 14.5 degrees C. However, the model is deficient in that it does not include clouds. So in the next section, clouds are integrated into the model. The cloud coverage of the Earth is represented by the cloud fraction. This cloud fraction influences the surface energy balance by separating the heat emission incident on the surface into an atmospheric portion and a cloud portion. The clouds also affect the solar energy incident on the surface in the surface energy equation. For the atmospheric energy balance, the equation expands as well to include emission from the top and bottom of the clouds. Transmission through the clouds and solar absorption by the clouds are also integrated. Two new temperatures are introduced, the top of the cloud temperature and the bottom of the cloud temperature. The problem has 6 unknowns and 3 equations. However, looking at empirical data, the cloud fraction does not vary significantly throughout the year. The average is about 67%, with a variation of 1 to 2% throughout the year, month to month. Therefore, the cloud fraction equation, which is the fourth equation in the model, assumes that the cloud fraction is constant at 67%. Since the cloud fraction is stable, the solution is named the stability solution. The stability assumption is that all temperatures and fluxes are minimized at thermal equilibrium, and the change in temperature and heat flux with cloud fraction is zero at a cloud fraction of 67%. Here are the first three equations in the model. The fourth equation is the cloud fraction. The only change to the first three equations is the replacement of the atmospheric temperature with the temperature at the top of the clouds. The fifth and sixth equations are determined by differentiating the surface and atmospheric energy balances with respect to cloud fraction and setting the derivatives of temperature and heat flux equal to zero. Solving the system of equations for the unknowns yields the following temperatures and heat flux. The surface temperature is commensurate with the actual measured average surface temperature of the Earth of 14 degrees Celsius. The other temperatures correspond well with the heat emission map from NASA near-Earth observations shown here and seen before. An uncertainty analysis is applied to the surface temperature to determine its accuracy. Each parameter is an estimate with an assumed uncertainty in value given as shown. The surface temperature uncertainty is estimated at plus or minus 3.8 degrees Celsius. If the modeling was depicted, the model started with a surface temperature of 1 degree Celsius using the gray body energy balance. When nitrogen and argon are added, the temperature decreases due to Rayleigh scattering, reflecting sunlight. Adding oxygen to the problem increases atmospheric heat and solar absorption through the conversion of oxygen into ozone. This increases the surface temperature slightly, but also increases the atmospheric temperature due to the energy absorbed. Adding water to the problem leads to additional atmospheric solar and heat absorption, as well as evaporation and convection and cloud formation. Finally, adding carbon dioxide increases heat and solar absorption, leading to a higher surface and atmospheric temperature. The final surface temperature is comparable to the measured surface temperature, and the uncertainty bars are added for completeness. Finally, each parameter in the model is modified to cause a 1 degree Celsius increase in surface temperature. The relative effects of these individual parameters are shown. Each parameter is changed individually. So, for example, when evaluating the surface emissivity, the emissivity value of 0.96 is reduced to 0.928, causing a 1 degree Celsius increase in surface temperature. If we evaluate the surface solar reflection alone, we change the surface emissivity back to 0.96 and then change the surface solar reflection from 0.10 down to 0.08 to cause the same 1 degree increase in surface temperature, and so on and so forth for the other parameters. To conclude, the standard climate claims are deficient, and the stability solution, albeit not perfect, is far superior to the conventional climate modeling. Using the stability solution model, the claims are corrected as follows. My future work includes honing the atmospheric and solar absorption parameters using additional models and applying the stability solution and absorption models to further evaluate the climate. The goal is to provide conclusive evidence validating or invalidating climate claims. I'd like to acknowledge NASA Near Earth Observations website for the satellite data and images utilized in this presentation. Thank you for listening, and if you'd like to read the entire article, go to prosejournals.com.